Right now, as you sit here, a flood of tiny particles is streaming through your body. They come from the sun, and they pass through your hand, your chair, the floor, and the whole solid earth as if none of it were there. About 100 trillion of them cross through you every second, and you never feel a single one. These are neutrinos, the lightest particles of matter we know, and for a long time we were sure they weighed nothing at all. They do have weight, a tiny, stubborn sliver of mass, and that one fact quietly breaks the rulebook physicists spent a century building. If you enjoy following a mystery down to its root, take a moment to subscribe and stay with me. Here is the simple question we will follow. How can something so close to nothing be the first solid sign that our best theory of matter is not the whole story? Hold out your hand for a moment and look at it. It feels solid. The skin, the bone, the warmth underneath, all of it seems firmly there. And yet right now, a river of particles is pouring straight through that hand without touching anything at all. They come mostly from the sun, streaming out of its core, crossing 93 million miles of empty space, and arriving here in a little over 8 minutes. About 100 trillion of them pass through your body every second. They go through your hand, your chair, the floor, the rock beneath the building, and out the far side of the planet. And you feel nothing, nothing at all. These are neutrinos, and they are the faintest, shyest particles of matter we have ever found. For most of the last century, physicists were sure of one clean fact about them. They were sure the neutrino weighed nothing, that it was a particle with no mass, moving at the speed of light and carrying no weight of its own. That belief was written into the foundation of our best theory of matter, the theory we call the Standard Model. And it was wrong. The neutrino does have weight. It carries a tiny, stubborn sliver of mass, far smaller than anything else we can measure, and that one small fact does something remarkable. It opens a crack in the theory that physicists spent 100 years building. It is the first solid sign found in experiment after experiment that the Standard Model is not the final word. The whole story we are about to follow is the story of how a particle that barely exists became the most reliable pointer we have toward physics we do not yet understand. It is a slow story, and I want to build it up carefully, one piece at a time, so that by the end you can hold the whole shape of it in your mind. We will not rush. We will start where the physicists started, with a problem that looked at first like nothing more than a bookkeeping error. Because that is how the neutrino entered the world. It was never seen, never caught, never even suspected from a track in a detector. It was invented on paper to fix a broken sum. Some energy had gone missing in the laboratory, and the missing energy would not come back. And the law that said it could never vanish was one of the deepest laws in all of physics. Someone had to choose. Either the law was broken, or something invisible was carrying the energy away. The particle we now know as the neutrino was the guess that saved the law. And the strange thing, the thing worth sitting with, is that this ghostly guess turned out to be real, and then turned out to be far more important than anyone who guessed it could have known. A particle proposed to patch a small hole in the accounting has ended up pointing beneath the whole structure. To see how that happened, we have to go back to the years when physicists were first learning to take atoms apart, when they watched certain atoms fall to pieces on their own and tried to measure exactly what came out. What came out did not add up. Energy went in, and less energy came out, and the difference had no home. That gap, small and quiet and impossible to ignore, is where everything begins. So let me take you there, into the confusion of the 1920s, into a phenomenon called beta decay, where the ledger of physics simply would not balance, and where a few careful people refused to look away from a number that should not have been possible. An atom's nucleus is not always still. Some kinds of atoms are unstable, and every so often one of them breaks its own balance and changes into a different element. This is radioactivity, and by the early 1900s physicists had sorted it into a few types. One of them was called beta decay. In beta decay, a nucleus spits out a fast-moving particle, an electron, and in doing so turns one of its neutrons into a proton, nudging itself one step up the ladder of elements. That much they could see. The electron came flying out, and they could catch it and measure its energy. And here is where the trouble started. When a nucleus decays this way, it drops from one fixed energy level to another fixed energy level. The difference between those two levels is a set amount, the same every time for the same kind of atom. So the electron that carries the difference away should always come out with the same energy. Every electron from the same decay should be a twin of the last, each one carrying the same fixed share. That is what the law of conservation of energy demanded. Energy cannot be created or lost, it can only move from one form to another. So the books had to balance, electron for electron, every single time. When they measured it, the books did not balance. In 1914, a physicist named James Chadwick, working in Germany, looked carefully at the electrons coming out of beta decay and found something that made no sense. The electrons did not all carry the same energy. They came out with a whole smear of energies, a continuous spread from almost nothing up to a maximum. Some electrons carried the full share the law demanded. Most carried less. A great many carried far less, and where that missing energy had gone, no one could say. Picture paying out the same wage to 100 workers, the same fixed sum owed to each. But when you check the envelopes, only a few hold the full amount. Most hold less, some almost empty, and the shortfall differs from envelope to envelope with no pattern you can name. The money owed was fixed. The money delivered was not. Somewhere between the ledger and the hand, a portion kept slipping away. That was beta decay. This was not a small discrepancy that better instruments would clean up. Careful measurement only made it sharper. The energy of the outgoing electron was genuinely variable, and it was almost always short of the mark. The nucleus dropped by a fixed amount, yet the electron carried away a changing, usually smaller amount, and the difference had simply disappeared. For more than a decade, this sat like a stone in the middle of physics. It was not a minor puzzle at the edge of the field. It struck at conservation of energy itself, one of the most trusted principles in all of science, the rule that lets you trust any calculation about anything. If energy could quietly vanish inside an atom, then the ground under every other law began to feel unsteady. Some of the greatest physicists of the age were prepared to consider the unthinkable. Niels Bohr, one of the founders of quantum theory, began to wonder aloud whether conservation of energy simply failed inside the nucleus, whether it held only on average and not in each single event. That was how serious the crisis had become. A man who had helped build the new physics was ready to loosen one of its deepest laws to make the numbers fit. Most were not willing to go that far. Giving up conservation of energy felt like giving up the game itself. And so the question hung there, unanswered and heavy, waiting for someone to find a way to keep the law and still explain the missing energy. The answer, when it came, would not arrive from a new experiment. It would arrive in a letter. In December of 1930, a group of physicists gathered in the German town of Tübingen to talk about radioactivity. one of the most brilliant minds of the age was not there. Wolfgang Pauli, an Austrian physicist known for his sharp tongue and his sharper thinking, had stayed away. He sent a letter instead, and it has become one of the most famous letters in the history of science. He opened it, half joking, with the greeting, "Dear radioactive ladies and gentlemen." Then he laid out an idea he himself called a desperate remedy. Pauli proposed that the missing energy in beta decay was not missing at all. It was being carried off by a particle no one had ever seen, a particle so faint and so hard to catch that it slipped out of every experiment unnoticed. When a nucleus decayed, he suggested, it threw out not one particle, but two. There was the electron they could measure, and there was this second hidden particle they could not. Between them, the two would share the energy of the decay. Sometimes the electron took more, sometimes less, and the invisible partner took whatever was left. Add the two together and the sum would always come out fixed, exactly as the law required. The books balanced again. The energy was never lost, it was only hidden in a particle that refused to be seen. For this to work, the new particle had to be strange in a very particular way. It had to be electrically neutral, carrying no charge, or the experiments would already have spotted it pulling on electric and magnetic fields. It had to be extraordinarily light, lighter than anything then known. And it had to barely interact with ordinary matter at all, passing through detectors like they were not there, which is exactly why it had gone unnoticed for so long. Pauli called his invented particle the neutron, using a name that would soon belong to something else. He was uneasy about the whole thing. He had proposed a particle that, by its very nature, might be impossible to ever detect, and to a physicist that felt like cheating. He is said to have told a friend, with real regret, that he had done a terrible thing by predicting a particle that could not be found. A theory you can never test is barely a theory at all. Think about what he was actually doing. He was staring at a hole in the accounts, a real and measured shortfall, and rather than accept that energy could vanish, he chose to fill the hole with something invisible. It was a bold move, and it could easily have been wrong. Physics is full of invisible fixes that turned out to be nothing, patches invented to save a theory that simply needed replacing. Pauli knew this. That is why he called it desperate. He was trading one uncomfortable idea, the loss of energy, for another, a ghost particle that might never show its face. But the trade had one great virtue. It kept conservation of energy intact. It let physicists go on trusting the deepest law they had, and it did so with a clear, testable claim. Somewhere in every beta decay, a light neutral, barely interacting particle was slipping away with the missing energy. For a few years the idea sat quietly, more a clever suggestion than an accepted fact. Pauli had given the crisis a possible answer, but he had not given it a full theory, and he had not given the particle a proper name or a proper place in the equations. That work fell to someone else, a young Italian physicist with a gift for turning loose ideas into hard mathematics. He would take Pauli's ghost, give it a name that stuck, and build around it a theory of beta decay so good that it is still taught today. The young physicist was Enrico Fermi, working in Rome in the early 1930s, already known as one of the finest minds in Europe, and rare among physicists for being brilliant at both theory and experiment. Fermi took Pauli's rough idea and did something with it that Pauli had not. He built it into a full mathematical theory of how beta decay works. First, he gave the particle a name. By the time Fermi took up the problem, the name neutron had been claimed. In 1932, the English physicist James Chadwick, the same man who had studied beta decay years earlier, discovered a real, heavy, neutral particle inside the nucleus. And that particle became the neutron we know today. Pauli's little ghost needed its own word. Fermi, speaking Italian, called it the neutrino, which means roughly the little neutral one. The neutron was the big neutral particle in the nucleus. The neutrino was its tiny, elusive cousin. The name stuck, and it has been the neutrino ever since. Then came the real work. In 1933 and 1934, Fermi wrote down a theory of beta decay that treated it as a brand new kind of process. In his picture, a neutron inside the nucleus transforms into a proton, and in that instant of transformation, it creates two particles out of the energy of the change. It creates the electron that flies out, and it creates a neutrino that flies out alongside it. The two were born together in the act of decay, and together they carried away the released energy, sharing it between them in the smooth, variable way the experiments had shown. Fermi's theory did something a good theory should. It did not just tell a story, it predicted numbers. It gave the exact shape of the energy spread, the smear of electron energies that had so puzzled everyone. It said how the number of electrons at each energy should rise and fall across the range, and when physicists checked that predicted shape against the real measurements, it fit. The strange smear was no longer a mystery. It was the natural signature of energy being split between an electron and a neutrino, exactly as Fermi's equations described. There was also a deeper idea hidden in the mathematics. To make his theory work, Fermi had to introduce a new force. The forces known at the time, gravity and electromagnetism, could not drive this kind of transformation. Beta decay needed something else, a new and feeble interaction working only at the tiniest distances inside the nucleus. Today we call it the weak nuclear force, and it is one of the four fundamental forces of nature. The neutrino, it turned out, feels only this weak force and gravity, and nothing else. That is the deep reason it is so hard to catch. It is deaf to the electric force that governs almost everything in ordinary matter. Fermi was proud of the work, and he was right to be. His theory of the weak interaction was so well built that its core survives, refined but recognizable, in physics today. Yet when he tried to publish his first paper on it in the leading journal Nature in 1934, the editors turned it down. They judged it too speculative, too far from anything that could be observed, too remote from physical reality. It is one of the more famous rejections in science. The theory they waved away became a cornerstone of modern physics. So by the mid-1930s the neutrino had a name, a theory and a clear job. On paper it was solid. But it was still only on paper. No one had ever seen one. And by Fermi's own theory, seeing one looked almost hopeless, because the same weakness that let the neutrino balance the books also let it pass through nearly anything without leaving a trace. Just how hard is it to catch a neutrino? The honest answer is that it is harder than almost anything else in physics, and it helps to sit with just how extreme the difficulty is. A neutrino feels only two of the four forces of nature. It feels gravity, which for a single particle this light is almost nothing, and it feels the weak nuclear force, the same force that drives beta decay. The weak force earns its name. It reaches only across the tiniest distances, far smaller than an atom, and it acts only when a neutrino passes almost directly through a nucleus, close enough to touch. The rest of the time, the neutrino simply ignores matter. It does not feel the electromagnetic force, so it never pushes on electrons or gets pushed by them. It does not feel the strong force that binds nuclei together. To a neutrino, ordinary matter is almost entirely empty space, and even the parts that are not empty are nearly invisible to it. To put a number on it, imagine you could build a solid wall of lead and send a neutrino at it. To have an even chance of stopping a single neutrino from the sun, That wall of lead would need to be about a light year thick. Light travels for a full year to cross 1 light year at 186,000 miles every second. A wall of solid lead that deep, and the neutrino still has only a 50-50 chance of being caught inside it. Everything thinner, and it most likely sails straight through. The whole Earth, 8,000 miles of rock and metal from one side to the other, is nothing to it. Almost every neutrino that reaches our planet goes clean through and out the other side, as if the planet were a thin morning mist. This is why Pauli was so uneasy. He had proposed a particle that might, by its very nature, be impossible to detect. If a neutrino can cross a light year of lead, how could anyone ever hope to catch one in a laboratory that fits inside a building? The particle seemed designed to escape, and yet there was a thread of hope, and it lay in sheer numbers. A single neutrino almost never interacts, but the sun pours out neutrinos in unimaginable floods, and certain human machines make them too. If you cannot raise the odds for one neutrino, you can pile up the neutrinos instead. Send enough of them through a large enough target, and the laws of chance turn in your favour. Out of trillions upon trillions passing through, once in a great while, one will strike a nucleus dead on and leave a mark. The trick is to have so many neutrinos, and so many nuclei waiting, and a detector patient enough that a handful of those rare collisions can be seen and trusted. That is the whole strategy of neutrino detection, and it has not changed. You do not catch the neutrino by being clever with a single one. You catch it by flooding a huge, still target with an ocean of them, and watching, for a long time, for the rare flash when one finally connects. Everything depends on having a strong enough source and a big enough detector, and on shielding it so well that the few real signals are not drowned in noise. For 2 decades after Fermi named it, no one had a source strong enough or a detector good enough to try. The neutrino stayed a creature of theory, real in the equations, unproven in the world. Then, in the years after the Second World War, a new kind of machine appeared, one that produced neutrinos in numbers no natural source on Earth could match. The nuclear reactor, built to release the energy of splitting atoms, also poured out a torrent of neutrinos as a side effect, and beside one of these reactors, 2 determined physicists decided to try to catch a ghost. The 2 men were Clyde Cowan and Frederick Reines, working at the Los Alamos Laboratory in the United States in the 1950s. Reines was the driving force, a physicist who wanted to solve a problem that everyone else thought was impossible, precisely because it was impossible. Catching the neutrino was, to him, the ultimate challenge, and he found in Cowan a partner willing to chase it. They gave their effort a fitting name. They called it Project Poltergeist, after the unseen spirit that moves through a house and rattles it without ever being caught. Their plan rested on the strategy of overwhelming numbers. A nuclear reactor, they knew, was a furnace of beta decays, and so it poured out neutrinos, or more precisely antineutrinos, in staggering quantities. Every second a reactor sends out uncountable trillions of them. If you placed a large detector right up against the reactor wall, you would have the strongest neutrino source humans had ever assembled, driving a flood through your target every moment. The odds for any one neutrino were still almost nothing, but with that many passing through, a few would surely strike. The detector itself was the clever part. They built tanks filled with water and dissolved cadmium in the water to help the trap work. When a reactor antineutrino, once in a great while, struck a proton in the water, it triggered a specific reaction called inverse beta decay. The proton turned into a neutron, and a particle called a positron flew out, the antimatter twin of the electron. That was the key. This reaction left not one signal but 2, arriving in a precise sequence. First, the positron would meet an ordinary electron and the two would annihilate, vanishing in a burst of light with an exact known energy. Then, a few millionths of a second later, the freed neutron would drift through the water until a cadmium nucleus swallowed it, and that capture released a second, separate flash of light. Two flashes, of the right energies, separated by the right tiny gap in time. That double signature was a fingerprint that nothing else could easily fake. Random background noise might make one flash, but it would almost never make both, in the right order, with the right delay. By watching for that exact 1-2 pattern, Cowan and Reines could pull the whisper of a real neutrino out of the roar of everything else. They tried first in 1953 at the Hanford reactor, and the results were suggestive but not clean enough to trust. Too much background noise crept in. They rebuilt, improved the shielding, and moved to a more powerful reactor at the Savannah River site. There, in 1956, after years of effort, the signal came through clear. The double flashes appeared, at the right energies, with the right delay, and at the right rate. When they turned the reactor off, the signal faded. When it ran, the signal returned. They were catching neutrinos, a few each hour, out of the trillions upon trillions streaming through. 26 years after Pauli invented it in a letter, the ghost had been caught. Cowan and Reines sent Pauli a telegram to tell him that his particle was real, that the neutrino they had all doubted could ever be seen had finally left its mark in a detector. Pauli, the story goes, celebrated with a bottle of champagne. The particle proposed as a desperate remedy. The fix that might never be tested was now a measured fact of nature. Frederick Reines would eventually receive the Nobel Prize in 1995 for the discovery, though only decades later, and sadly after Cowan had died. The neutrino was no longer a guess, it was a confirmed piece of the world, and physicists could begin to ask what place it held among all the other particles. By the time the neutrino was caught, physicists were busy building the grand map of matter that we now call the Standard Model. It is the theory that lists every fundamental particle and every force except gravity, and describes how they all fit together. It is one of the great achievements of the human mind, and it has passed test after test with astonishing accuracy. When the Standard Model was assembled, the neutrino was given a clear seat at the table. In this map, matter is built from two families of particles. There are the quarks, which clump together to make protons and neutrons, and there are the leptons, the particles that live on their own. The electron is a lepton. The neutrino is a lepton too, the electron's quiet, neutral companion. Where the electron carries a negative charge and can be pushed and pulled by electric forces, the neutrino carries no charge and feels almost nothing. They are partners. In beta decay, an electron and a neutrino are born together, and that pairing runs all through the theory. So the neutrino settled into the Standard Model as one of its basic building blocks, a genuine fundamental particle, not made of anything smaller. And in this beautiful, successful theory, the neutrino was given one very specific property, written in from the start. It was assigned a mass of exactly 0. This was not a careless guess. There were reasons for it. In the 1950s, experiments had revealed something deeply strange about the neutrino, a property called handedness. Every neutrino ever seen spins in the same sense relative to its motion, like a screw that only ever turns one way. Physicists call this being left-handed. The antineutrino, its antimatter twin, is always right-handed. No one ever found a right-handed neutrino or a left-handed antineutrino. They simply were not there. This one-handedness fit together with a massless neutrino in a very neat way. A particle with no mass must travel at exactly the speed of light, and a particle moving at the speed of light can have its handedness fixed forever, the same for every observer, because nothing can ever catch up to it and see it from the other side. If the neutrino had even a little mass, it would travel a touch slower than light, and then in principle you could outrun it, overtake it, and see its spin appear to flip from one-handedness to the other. The clean, unbroken one-handedness of the neutrino seemed to demand that it be massless, so the standard model took the neutrino to be exactly massless, moving at light speed, purely left-handed, forever. It was the simplest choice, it matched what the experiments showed, and it made the mathematics tidy. For decades this stood as settled fact. Every textbook taught it. The neutrino was the one particle of matter with no weight at all, a thing of pure motion and no substance. Hold on to this, because it is the hinge of the whole story. The masslessness of the neutrino was not a small footnote. It was built into the foundation of our best theory of matter. It shaped the equations. It reflected the deep symmetry of the weak force. And it was, everyone agreed, one of the surest things we knew. So when the evidence finally arrived that the neutrino does have mass, however tiny, it did not just add a small number to a table. It reached down into the foundation and revealed a crack. It said, plainly, that the standard model was incomplete, that it had gotten one of its basic ingredients wrong. But that revelation was still decades away. Before it could come, physicists first had to discover that the neutrino was not alone. There was not one neutrino in nature, there were more. The first hint that the neutrino had relatives came from a different particle entirely, a heavy, unstable cousin of the electron called the muon. The muon had been discovered back in the 1930s in the rain of particles that space sends down onto the Earth, the cosmic rays. It behaved exactly like an electron in every way but one. It was about 200 times heavier, and it was unstable, living for only a couple of millionths of a second before falling apart. When a muon decayed, it too produced neutrinos, and this raised a sharp question. Was the neutrino that came from a muon the same as the neutrino that came from ordinary beta decay, the one paired with the electron, or was it something different, a second kind of neutrino, tied to the muon the way the first was tied to the electron? There were two clean possibilities, and only an experiment could decide between them. In 1962, 3 physicists at the Brookhaven National Laboratory in New York set out to find the answer. They were Leon Lederman, Melvin Schwartz, and Jack Steinberger. Their idea was to make the first ever beam of neutrinos on purpose, rather than waiting for the sun or a reactor. They took a powerful accelerator, smashed protons into a target, and produced a spray of particles that decayed in flight and threw off neutrinos. These neutrinos came from the decay of particles that also made muons, so if the neutrinos had a type, this beam would be full of the muon's kind. Then they let that beam strike a huge, dense detector and watched what came out when a neutrino finally interacted. Here was the test. If there was only one kind of neutrino in nature, then when these neutrinos struck the detector, they should produce electrons and muons in roughly equal measure. A neutrino is a neutrino, and it should not care which partner it makes. But if the neutrinos in the beam were a distinct second kind, tied specifically to the muon, then they should produce only muons, and no electrons at all. Each neutrino would remember where it came from, and make only its own partner. The result was clear. When the beam struck the detector, it produced muons, and only muons. Not a single electron appeared where the theory of one universal neutrino said there should be plenty. The neutrinos in the beam were not the same as the neutrinos of ordinary beta decay. They were a separate kind, bound to the muon, There were then at least 2 neutrinos in nature, and physicists gave them names to match their partners. The one born alongside the electron became the electron neutrino. This new one, born alongside the muon, became the muon neutrino. Each type is called a flavor, a slightly whimsical word for a serious idea. The neutrino came in more than one variety, and each variety was locked to its own charged partner. This discovery deepened the pattern of the Standard Model in a satisfying way. Matter seemed to come in repeating sets, in generations. The first generation held the electron and its electron neutrino, along with the lightest quarks. The second generation held the muon and its muon neutrino, with heavier quarks. It was as if nature had built the same basic kit more than once, each copy heavier than the last. For reasons no one could explain, Lederman, Schwartz and Steinberger received the Nobel Prize in 1988 for showing that the neutrino wore more than one face, and their discovery raised an obvious next question. If there were 2 generations, each with its own neutrino, and if a still heavier cousin of the electron and muon were ever found, then somewhere out there a third neutrino should be waiting. The partner of a particle not yet discovered. Nature, it seemed, might not have stopped at 2. The search for a third generation took decades to complete, and it came together in 2 stages. First, physicists had to find the heavier cousin of the electron and the muon. Then they had to catch its neutrino. The heavy cousin arrived in the 1970s. At the Stanford Linear Accelerator Center in California, a physicist named Martin Pearl and his team were sifting through the debris of high-energy particle collisions when they found signs of a new particle, heavier still than the muon. They called it the tau. It was the third member of the family, a lepton like the electron and the muon, but much more massive, about 17 times heavier than the muon, and very short-lived. Its discovery confirmed that nature had built the basic kit of matter a third time, and it carried an immediate implication. If the pattern held, the tau should have its own neutrino, a third flavour, the tau neutrino, born alongside the tau just as the other neutrinos were born beside their partners. For years the tau neutrino was accepted on the strength of the pattern alone. The symmetry of the Standard Model all but demanded it, and other measurements pointed the same way. In particular, experiments studying the decay of a heavy particle called the Z boson showed how many light neutrino types can exist in nature. The Z boson can decay into neutrinos, and the more kinds of light neutrino there are, the faster it falls apart. When physicists measured its lifetime carefully at the Large Collider at CERN in Europe, the answer came out clean and sharp. The number of light neutrino flavors was 3. Not 2, not 4. 3, and the measurement was precise enough to be sure. So even before anyone caught a tau neutrino directly, there was strong reason to believe it existed, and that the family was complete at 3. Still, physicists wanted to see it, to catch a tau neutrino in the act and confirm it the hard way. Catching it was especially difficult. A tau neutrino, when it interacts, produces a tau particle, and the tau is so heavy and so short-lived that it travels only a tiny distance before decaying, leaving a very short track that is easy to miss. It took a special experiment to see it. That experiment was called Donut, run at the Fermilab Laboratory near Chicago. It used a detector built from fine layers of photographic emulsion, able to record particle tracks with extraordinary precision, fine enough to catch the tiny telltale kink where a tau appeared and then decayed. In the year 2000, the Donut team announced success. They had directly observed the tau neutrino, catching a handful of clean events where a tau neutrino struck the detector and made a tau. With that, the neutrino family was complete, confirmed on all 3 counts. there were exactly 3 flavors of neutrino, matched 1-to-1 with the 3 charged leptons. The electron neutrino with the electron, the muon neutrino with the muon, the tau neutrino with the tau. 3 generations of matter, 3 neutrinos, each locked to its own partner and no more. This was a moment of real completeness for the Standard Model. The map was filling in exactly as the theory predicted, generation by generation, particle by particle. And through all of it, one property of the neutrino stayed fixed in the equations. All 3 neutrinos were still taken to be massless, weightless things of pure motion. That assumption had not yet been challenged. But the challenge was already gathering, and it was coming from an unexpected direction, not from a collider or a reactor, but from the sun itself, and from a physicist who had done nothing more than count, very carefully, how many neutrinos the sun should send us. The sun shines because deep in its core, hydrogen is being fused into helium. Under crushing pressure and enormous heat, protons are forced together, and step by step they build up into helium nuclei, releasing energy that works its way out over thousands of years and finally leaves the surface as sunlight. That is the furnace that warms the Earth. And that same furnace, running every second in the heart of the sun, produces neutrinos as a direct part of the reaction. Every time protons fuse and turn into the building blocks of helium, neutrinos are made and flung outward. These are electron neutrinos, born in the nuclear fire at the sun's centre. Unlike the light, which takes ages to struggle out through the dense layers above, the neutrinos leave almost at once, streaming straight out through the whole body of the sun, as if it were transparent, and crossing space to reach us in a little over 8 minutes. They are a direct message from the core, carrying news of the fusion happening right now, deep inside a place we can never see. In the 1960s, an American astrophysicist named John Buckle set out to calculate exactly how many of these solar neutrinos should be reaching the Earth. It was a formidable piece of work. He had to model the inside of the sun in detail, its temperature, its density, its composition, and the full chain of nuclear reactions taking place there. He had to work out which reactions made neutrinos, how many, and with what energies. Buckle became the world's expert on the inner workings of the sun, and his calculation of the solar neutrino flux was a landmark, refined again and again over the years. The number was staggering. Buckle found that the fusion in the sun should send an immense torrent of neutrinos through every part of the Earth. On the order of tens of billions of solar neutrinos should pass through every square centimetre of ground, every second, day and night, whether the sun is overhead or on the far side of the planet, because the Earth is no barrier to them at all. This is the source of the 100 trillion neutrinos passing through your body each second. It is the sun's fusion, translated into a number, streaming through you and everything around you without pause. Buckle's calculation did something important. It turned the neutrino from a laboratory curiosity into a tool. If you knew how many neutrinos the sun should produce, and you could measure how many actually arrived, then you could test your understanding of the sun itself. You could look straight into the core of a star through the neutrinos it sent and check whether your picture of how stars burn was correct. It was a bold and beautiful idea. The neutrinos would let us see inside the sun, but it depended on 2 things matching: the number Buckle calculated on paper and the number an experiment actually caught. If they agreed, it would be a triumph, confirming both the theory of the sun and the theory of the neutrino in one stroke. To make the test real, someone had to build a detector that could catch solar neutrinos and count them. That someone was a chemist named Raymond Davis, and he was about to go deep underground with a tank the size of a swimming pool to try to catch the ghosts of the sun. What he found would not match Bachel's number, and the gap between them would open into one of the great mysteries of 20th century physics. Raymond Davis built his detector nearly a mile underground in the Homestake gold mine in South Dakota. It had to be that deep to hide it from the constant rain of cosmic rays that would otherwise swamp the delicate signal. A mile of solid rock overhead acted as a shield, blocking almost everything except the neutrinos, which passed through the rock as easily as through open air. Down in that mine, Davis installed an enormous tank holding about 100,000 gallons of a common cleaning fluid, a chemical rich in chlorine. His method was patient and ingenious. Every so often, very rarely, a solar neutrino passing through the tank would strike a chlorine atom and turn it into a special form of argon, a different element. Each captured neutrino left behind a single atom of this argon. Davis's task was to let the tank sit for weeks, gathering these argon atoms one by one, and then to flush the entire tank and extract the mere handful of argon atoms that the neutrinos had created out of the countless trillions of other atoms in the fluid. It was chemistry of almost unbelievable delicacy, finding a few dozen special atoms in a tank the size of a swimming pool and counting them. Davis ran his experiment through the late 1960s and on for years afterward, and when he counted the neutrinos the sun was sending, he found far too few. He measured only about a third of the number Bachel's calculation predicted. 2 out of every 3 solar neutrinos that should have arrived were simply not there. Where the theory said the tank should catch a certain number of neutrinos, Davis caught roughly 1 in 3, again and again, year after year. This was the solar neutrino problem, and it was a genuine puzzle that would last for more than 30 years. 2 of the most careful scientists of their time had each done excellent work. Backel had calculated how many neutrinos the sun makes. Davis had measured how many arrive. And the 2 numbers did not agree. The measurement came out at about a third of the prediction, a gap far too large to shrug off. At first, almost everyone assumed one of the 2 men had simply made a mistake. Perhaps Bachel's model of the sun was off, its core a little cooler than he thought, producing fewer neutrinos. The neutrino output depends very steeply on the sun's central temperature, so even a small error there could change the number a great deal. Or perhaps Davis's fiendishly difficult experiment was losing neutrinos somehow, missing some of the argon atoms, undercounting the real signal. For years the 2 possibilities hung side by side, and the natural expectation was that better work would close the gap. But the gap did not close. Backel checked and rechecked his solar model, and other astronomers tested the sun in independent ways, and his calculation held up. The sun really did seem to be producing the number of neutrinos he had figured. Davis refined his experiment, and other groups built different detectors using different methods, sensitive to neutrinos of different energies, and they too found a shortfall. The neutrinos really were arriving in smaller numbers than the sun should send. Both men were right. The sun made the neutrinos Backel calculated, and only a third of them reached Davis's tank. The missing 2/3 had gone somewhere between the core of the sun and the bottom of a mine in South Dakota. Something was happening to the solar neutrinos on their journey, something no one yet understood, and the answer would turn out to reach far deeper than anyone counting atoms in a tank could have guessed. For the solar neutrino problem to be a true mystery, and not just a mistake somewhere, physicists had to close off the easy escapes one by one. The first suspicion always fell on the sun. Maybe John Bachel's model was simply wrong. The number of neutrinos a star produces depends very sensitively on the temperature at its core, so steeply that a change of just a few % in that temperature would change the neutrino count by a large amount. Perhaps the sun centre was slightly cooler than Barkul thought, and there was no real mystery at all, only an overestimate. This possibility was taken seriously, and it was tested hard. Over the following decades, a whole field grew up devoted to studying the inside of the sun through the way it vibrates, a field called helioseismology. The sun rings very faintly like a bell, with sound waves rolling through its interior, and by watching how its surface trembles, physicists can map the temperature and density deep inside with real precision. When they did this, Barkul's model of the solar interior held up beautifully. The sun's core was just about as hot as he had calculated. The star was not the problem. Barkul had gotten it right. The next suspect was Davis's experiment. Catching a few dozen atoms of argon in a swimming pool of cleaning fluid is desperately hard, and it would be easy to imagine losing some along the way, undercounting the true number. But this escape was closed off too by other experiments. Different teams built entirely different detectors using different target materials sensitive to neutrinos of different energies. Some used gallium, which could catch even the low-energy neutrinos from the main fusion reaction of the Sun. Later, a huge detector in Japan called Kamiokande watched for solar neutrinos in yet another way, by catching the faint flashes of light they made in a great tank of pure water. All of these experiments, using different methods and different materials, saw the same thing. They all caught fewer solar neutrinos than the Sun should be sending. The exact size of the shortfall varied with the energy of the neutrinos each experiment could see, which was itself a clue, but the deficit was always there. The problem was not a flaw in one tank. It was real, and it was consistent across the whole field. So both easy answers failed. The Sun was fine. The experiments were fine. The neutrinos really were going missing, in a pattern too steady and too widespread to be an error. That left a stranger and more uncomfortable conclusion. If the Sun makes a certain number of electron neutrinos, and only a fraction of them arrive as electron neutrinos, then something must be happening to them in between. The neutrinos were not being destroyed, since energy still had to be conserved. They were somehow escaping detection. And there was one way that could happen. The detectors in these experiments were mostly built to catch electron neutrinos, the kind the Sun makes. What if the electron neutrinos were changing on the way, turning into one of the other flavors? The muon neutrino or the tau neutrino, which those detectors could not see? Then the neutrinos would not be missing at all. They would simply have changed their coats, slipped into a form the experiments were blind to, and passed through uncounted. It was a bold idea, and it required the neutrino to do something no one had ever seen a particle do. It required a neutrino to change its very identity in mid-flight, to leave the Sun as one flavour and arrive as another. And that strange idea had already been proposed, years earlier, by a physicist working almost alone on the possibility that the neutrino could transform. The physicist was Bruno Pontecorvo, one of the most original and unusual figures in the whole story of the neutrino. He had been a student of Enrico Fermi in Rome, one of the bright young men in Fermi's group, and he spent his life thinking about neutrinos more deeply than almost anyone. His life took a dramatic turn in 1950, when he vanished from the West and reappeared in the Soviet Union, where he continued his work for the rest of his career. Cut off from many of his former colleagues, he kept following his own ideas about the particle he understood so well. Pontecorvo's great idea was that a neutrino might not keep a fixed identity. It might be able to change from one flavour into another as it travelled. An electron neutrino, born in the Sun, might turn partway into a muon neutrino, or a tau neutrino, and then perhaps back again, oscillating between the flavours as it flew through space. He worked this idea out over the 1950s and 1960s, drawing on earlier hints, and built it into a real theory of what came to be called neutrino oscillation. The picture is genuinely strange, and it helps to hold it gently at first. We are used to a particle being one thing. An electron is an electron. It does not turn into something else as it moves along. But Pontecorvo proposed that the flavour of a neutrino is not a fixed permanent label. It is more like a note that can slide into another note. A neutrino that starts out purely as an electron neutrino could, after travelling some distance, be found as a muon neutrino instead. Wait a little longer, let it travel farther, and it might slide back toward electron neutrino again. The flavour oscillates back and forth as the neutrino moves, like a slow beat. If this were true, it would explain the solar neutrino problem perfectly. The Sun makes electron neutrinos. They set out toward Earth. On the long journey across space, they oscillate, and by the time they arrive, they are spread across all three flavours. Only a fraction are still electron neutrinos. Davis's detector and the others could mostly see only electron neutrinos, so they caught only that fraction and reported a shortfall. The other 2/3 were still arriving, but wearing the other flavours, invisible to the experiments. The neutrinos were never lost. They had changed on the way. It was an elegant solution, and it matched the size of the deficit remarkably well. Roughly 1/3 of the neutrinos arriving as electron neutrinos was just what you would expect if they had spread themselves fairly evenly across the three flavours during the trip. Pontecorvo had, in effect, predicted the shape of the answer before the problem was fully understood, working far away and largely on his own. But oscillation carried a price, a quiet catch buried inside the beautiful idea, and it was this catch that would make the whole thing matter so much. For a neutrino to oscillate, for it to change flavour as it travels, the mathematics of quantum mechanics demands one specific thing. The different flavours must have different masses, and if the flavours have different masses, then the neutrino cannot be massless. At least some of the neutrinos must weigh something. The very mechanism that could solve the solar puzzle, if it were real, would prove that the Standard Model's assumption of a massless neutrino was wrong. To see why oscillation forces the neutrino to have mass, we have to look a little closer at what is really doing the travelling, and at the hidden layer of reality that lies beneath the flavours. To understand why changing flavour requires mass, we need one idea from quantum mechanics, and it is worth taking slowly. In the quantum world, a particle does not always have to be just one definite thing. It can exist as a blend, a combination of possibilities layered on top of each other, until something forces it to show a single face. The neutrino lives this double life more fully than almost any other particle, and the key is to separate two different things we might mean by which neutrino. One way to describe a neutrino is by its flavour. Is it an electron neutrino, a muon neutrino, or a tau neutrino? This is what an experiment sees when the neutrino interacts, because the flavour is tied to which partner it makes, an electron, a muon, or a tau. Flavour is the face the neutrino shows when it is created or caught. But there is another way to describe a neutrino, by its mass. A neutrino can also be thought of in terms of definite mass states, particles of a specific fixed weight. Physicists call these the mass states, and label them simply 1, 2, and 3 in order of their mass. These are the versions of the neutrino that have a clean, definite mass and that travel through space in a simple way. Here is the heart of it. The flavour states and the mass states are not the same thing. They do not line up one to one. Instead, each flavour is a particular blend of the three mass states, mixed together in fixed proportions. An electron neutrino is one specific combination of mass states 1, 2, and 3. A muon neutrino is a different combination of the same three. A tau neutrino is yet another. Every flavor is a chord, and the mass states are the individual notes that make it up. When the Sun makes an electron neutrino, it makes that particular chord of mass states. And now comes the reason oscillation happens. The three mass states, having different masses, travel through space at very slightly different rates. They move almost identically, but not quite, because their masses differ. As the neutrino flies along, the three mass states slowly drift out of step with one another, like three tuned strings struck together that gradually fall out of phase. The chord that started as a pure electron neutrino slowly shifts, because its ingredients are sliding relative to each other. After some distance, the same three mass states, now in a different arrangement, add up to a different chord, one that is mostly muon neutrino or tau neutrino. Detect the neutrino there, and you find a different flavour than the one that set out. Travel farther, and the arrangement keeps shifting, and the flavour oscillates onward. This is why the whole thing hangs on mass. The mass states drift out of step only because they have different masses. If all three had exactly the same mass, they would travel in perfect lockstep, never falling out of phase, and the chord would never change. The electron neutrino would stay an electron neutrino forever. And if the neutrino were truly massless, as the standard model assumed, there would be no distinct mass states at all to fall out of step, and no oscillation could ever happen. So the logic runs one direction with no escape. If neutrinos change flavour, then their mass states differ. If the mass states differ, the masses cannot all be zero. Therefore, the neutrino has mass. Oscillation and mass are bound together. You cannot have the one without the other. This meant the solar neutrino problem was not just a puzzle about the Sun. If the answer really was oscillation, then hidden inside that answer was a fact that would crack the foundation of particle physics. All that remained was to prove, beyond any doubt, that neutrinos truly oscillate. And the first clean, undeniable proof would come not from the Sun, but from the sky. The proof arrived in 1998 from a magnificent detector in Japan called Super-Kamiokande. It sits about half a mile underground in a zinc mine, and it is a wonder of engineering. Picture a vast cylindrical tank, tall as a 10-story building, holding 50,000 tons of ultra-pure water, its walls lined with more than 11,000 golden light sensors, each one watching the water for the faintest flash. When a neutrino interacts in the water, it can produce a charged particle that shoots forward faster than light travels through water. And this creates a faint cone of blue light, a kind of optical shockwave. The thousands of sensors catch that ring of light and record it, and from the pattern the physicists can read off what kind of neutrino it was and which way it was going. Super-Kamiokande was studying neutrinos made in the Earth's atmosphere. When cosmic rays from space slam into the upper air, they produce showers of particles, and among the debris are neutrinos, both muon neutrinos and electron neutrinos, in a well-understood ratio. These atmospheric neutrinos rain down from the sky all over the planet, and here the physicists saw their opportunity. Neutrinos are made all around the Earth, so the detector receives them from every direction. Some come straight down from the sky just overhead, having travelled only a few miles from where they were made in the atmosphere above. Others come up from below, having been made in the atmosphere on the far side of the Earth, and then passed all the way through the entire planet to reach the detector from underneath. The neutrinos coming down had travelled a short distance. The neutrinos coming up had travelled about 8,000 miles, the full width of the Earth. This gave the experiment a natural test of oscillation. Oscillation depends on distance. A neutrino changes flavour gradually as it travels, so neutrinos that had gone farther should show more change than neutrinos that had gone only a short way. If neutrinos oscillate, then the muon neutrinos coming up from below after their long journey through the Earth should be depleted compared to the ones coming straight down from above. Some of them would have oscillated into tau neutrinos along the way, which the detector could barely see. That is exactly what Super-Kamiokande found. The team, led by Takaaki Kajita, carefully counted the muon neutrinos coming from every direction. The ones arriving from overhead, having travelled only a short distance, came in close to the expected number. But the ones arriving from below, having crossed the whole Earth, were missing in large numbers. Only about half as many muon neutrinos came up from below as should have. They had vanished in transit, and the amount of vanishing depended cleanly on how far they had travelled, in just the way oscillation predicted. This was the discovery. The muon neutrinos were disappearing over distance, transforming into another flavour as they flew. Here at last was direct and convincing evidence that neutrinos oscillate, that they change flavour in flight. Seen not in the complicated environment of the Sun, but in neutrinos made right here in our own atmosphere, measured against the simple variable of distance travelled. Super-Kamiokande had caught the neutrino in the act of changing, and because oscillation requires mass, this was also the first strong evidence that the neutrino weighs something. The announcement in 1998 sent a charge through physics. The assumption of the massless neutrino, built into the standard model for decades, was cracking. But one piece of the puzzle was still missing. The atmospheric result showed muon neutrinos disappearing, yet it could not directly show what they turned into. To close the case completely, and to solve the original solar mystery for good, physicists needed to catch all three flavours and account for every neutrino. That final proof was waiting in a mine in Canada. The trouble with every solar neutrino experiment so far was the same. They could see only electron neutrinos, the kind the Sun makes. So a shortfall could always be read two ways. Either the neutrinos were truly being lost, which would break conservation, or they were changing into muon and tau neutrinos that the detectors were blind to. To end the argument for good, someone had to build a detector that could do two things at once. It had to count the electron neutrinos by themselves, and it also had to count all three flavours together, adding up every neutrino no matter what coat it wore. If the total came out equal to the number Bachel's Sun should make, while the electron neutrinos alone came out short, then the case was closed. The neutrinos were not vanishing, they were changing. That detector was the Sudbury Neutrino Observatory, and it sat about 1.5 miles underground in a working nickel mine near Sudbury. In Ontario, Canada, its secret was its target. Instead of ordinary water, it used 1,000 tons of heavy water, a rare and costly form of water in which each hydrogen atom carries an extra neutron, making a heavier twin called deuterium. Canada had a large supply of heavy water on hand from its nuclear program, and it lent this precious liquid to the experiment. The heavy water was the key, because the deuterium in it gave neutrinos two different ways to interact, and the two ways counted different things. In one kind of reaction, only an electron neutrino could take part, breaking the deuterium apart in a way that made an electron. This channel counted electron neutrinos alone, just like the older experiments, but there was a second kind of reaction, in which a neutrino of any flavour could split the deuterium by knocking its two pieces apart without caring which flavour it was. This second channel was democratic. It counted electron, muon and tau neutrinos all the same, adding them into one grand total. So the same tank, watched two ways, could weigh both numbers. It could see how many electron neutrinos arrived, and it could see how many neutrinos of all kinds arrived. The experiment was led by Arthur MacDonald, and it ran at the turn of the century. In 2001 and 2002, SNO announced its results, and they were exactly what the oscillation picture demanded. The number of electron neutrinos counted alone came in low, only about a third of what the Sun should send, just as Davis had found decades before. But the total number of neutrinos of all three flavours, counted together, came in right on the mark. It matched John Buckle's calculation of how many neutrinos the Sun produces, cleanly and convincingly. The missing 2/3 were not missing at all. They were there the whole time, arriving as muon and tau neutrinos, invisible to the old detectors, but caught by the all-flavour channel of the heavy water. This was the answer to a puzzle more than 30 years old. The Sun makes electron neutrinos, exactly as many as Buckle calculated. On the long flight to Earth, they oscillate, spreading out across all three flavours. By the time they reach us, only a third are still electron neutrinos, which is why Davis and the others always found a third. Both men had been right all along. Buckle's Sun was correct. Davis's count was correct. The gap between them was not an error in either one. It was the signature of the neutrino changing its identity in flight, hidden in plain sight for a generation. Sudbury closed the case. Between the atmospheric neutrinos of Super-Kamiokande and the solar neutrinos of SNO, oscillation was now proven from two independent directions, with two different sources at two different distance scales. The neutrino changed flavour, and that meant, beyond argument, that the neutrino had mass. The full weight of what that meant was about to be spelled out. The world of physics accepted the verdict quickly, because the evidence was so clean. Two great experiments working on entirely different neutrinos had reached the same conclusion by different roads. Super-Kamiokande had watched muon neutrinos from the atmosphere disappear over the width of the Earth. The Sudbury Neutrino Observatory had watched solar electron neutrinos reappear as other flavours, with the total conserved. Both pointed to the same fact. Neutrinos oscillate, and to oscillate, they must have mass. In 2015, the Nobel Prize in Physics was awarded for exactly this discovery. It went to Takaaki Kajita, who had led the atmospheric neutrino work at Super-Kamiokande, and to Arthur MacDonald, who had led the solar work at Sudbury. The prize was given in the plainest terms for the discovery of neutrino oscillations, which shows that neutrinos have mass. That short phrase carried an enormous weight, for it did something that had almost never happened in the long life of the Standard Model. It found the theory wrong. Remember how deeply the massless neutrino had been built in. The Standard Model did not merely fail to mention neutrino mass as an afterthought. It was constructed, from the ground, with the neutrino as a strictly massless particle, purely left-handed, moving at the speed of light forever. That choice was woven into its mathematics and tied to the deep structure of the weak force. So when the neutrino turned out to have mass, this was not a small correction that slid in quietly. It was the discovery that one of the foundation stones was the wrong shape. The Standard Model, the most successful and precisely tested theory in the history of science, was shown to be incomplete. It had gotten one of its own basic ingredients wrong. This is why the neutrino matters far beyond its own faint existence. Nearly everything else the Standard Model predicts is held up under the most punishing tests ever devised, sometimes matching experiment to 11 or 12 decimal places. The theory is almost frighteningly good. And yet here, in the lightest and shyest particle of all, it breaks. The neutrino is the one place where nature has plainly told us that our best theory is not the last word, that there is more physics beneath it. Waiting, this is the meaning of the title we set out to follow. The neutrino, by having mass at all, points beneath the standard model. It is a crack in an otherwise seamless wall, and physicists have been leaning into that crack ever since, trying to see what lies on the other side. The standard model itself cannot say why the neutrino has mass, or how much, or why that mass is so absurdly small. To answer those questions, the theory has to be extended, reached past, into new physics that no one has yet confirmed. So the discovery of neutrino mass was not an ending, it was a door. A very small door, opened by a very small particle, but a real one, and the first solid opening physicists have found in a theory that otherwise seems almost complete. Everything that follows in this story is about what we can see through that door. How heavy the neutrino actually is, and how we try to weigh a thing so light. Why it is so much lighter than everything else. Whether it might be its own antiparticle. And whether these ghostly particles, in the first moment of the universe, might be the reason there is any matter here at all, including you. The crack, once opened, runs deep. And the first thing to ask, now that we know the neutrino weighs something, is the most natural question of all. How much? Knowing that the neutrino has mass is one thing. Measuring that mass is another, and it is one of the hardest measurements in all of physics, because the mass is so vanishingly small. Oscillation, for all it proved, could not give the answer by itself. Oscillation depends only on the differences between the masses of the three mass states, not on the masses themselves. It is like hearing that three people differ in height by a few inches without being told how tall any of them is. The beats between the mass states tell you how far apart they are. They do not tell you where the whole set sits. So even after oscillation was proven, the actual weight of the neutrino remained unknown. To weigh it directly, physicists went back to where the whole story began, to beta decay. The idea is beautifully simple in principle. When a nucleus undergoes beta decay, it shares its energy between the electron and the neutrino. If the neutrino had no mass, the electron could, in the rare best case, carry away almost the entire energy of the decay, leaving the neutrino with nothing but motion. But if the neutrino has mass, then making that neutrino costs a little energy just to bring its mass into being, by the famous link between mass and energy. That tiny cost is subtracted from the electron, so the very fastest electrons, the ones at the extreme edge of the energy spread, can never quite reach the energy they would reach if the neutrino weighed nothing. The neutrino's mass carves a minute notch out of the top end of the electron energy spectrum. Measure the exact shape of that top edge precisely enough, and you can read off the mass of the neutrino. The trouble is the scale. The notch is fantastically small, because the mass is fantastically small, and only a handful of electrons ever land near that extreme edge. It takes an instrument of extraordinary delicacy to see it. The experiment built to do this is called Katrin, the Karlsruhe tritium neutrino experiment in Germany. It uses tritium, a heavy and unstable form of hydrogen that undergoes beta decay gently and often, making it ideal for the measurement. Tritium atoms decay and release electrons, and Katrin measures the energies of those electrons with almost unbelievable precision, focusing on the very highest energies near the edge. To do it, Katrin sends the electrons through a huge vacuum vessel that acts as an exquisite energy filter, sorting them by energy so finely that the faint distortion from the neutrino's mass can be seen. The main vessel is so large that when it was built in Germany, it could not fit through the roads by the direct route and had to travel a long way around by river and sea to reach the laboratory. A journey of thousands of miles for a trip that was only a short distance in a straight line. Katrin has now placed the tightest direct laboratory limit on the neutrino's mass. It has shown that the mass of the neutrino is below about 1 electron volt, in the units physicists use for such tiny weights. To feel that scale, the electron, itself a very light particle, is at least 500,000 times heavier than the neutrino's upper limit. The neutrino is not just light, it is lighter than anything else with mass by an enormous margin, a sliver of weight so small that the most refined direct experiment on Earth can so far only place a ceiling on it, not yet the value itself. And a direct scale is not the only way to weigh a ghost. There is another, stranger method, one that uses the entire universe as the balance. There is a way to weigh the neutrino that does not use any laboratory at all. It uses the whole sky and the way the universe has grown over billions of years. It sounds impossible that the faintest particle we know could leave a mark on something as vast as the cosmos, but it does, and the mark is real enough to measure. The reason lies in sheer numbers, and in the early universe. Neutrinos are, after the particles of light, the most abundant particles in existence. The whole universe is filled with them, left over from its first moments, hundreds of them in every small volume of space everywhere, a faint sea of neutrinos filling all of it. There are roughly as many neutrinos in the universe as there are particles of light, and both outnumber the atoms by more than 1 billion to 1. So even though each neutrino weighs almost nothing, there are so many of them that their combined mass adds up to something the cosmos can feel. Here is how they leave their mark. In the early universe, matter was spread almost perfectly smoothly, with only the faintest ripples of denser and thinner regions. Over time, gravity pulled the denser regions together, gathering matter into the galaxies and great clusters and vast webs we see today. This slow gathering of structure is one of the central stories of cosmology, and neutrinos interfere with it in a specific way. Because neutrinos are so light, they move extremely fast, close to the speed of light, for most of the history of the universe. Fast-moving particles do not settle easily into the growing clumps of matter. Instead, they stream freely out of them, smoothing over the smaller ripples before they can grow, like a breeze that keeps fine sand from piling into sharp dunes. The more mass the neutrinos carry, the stronger this smoothing effect, and the less sharply the small structures of the universe can form. So the pattern of galaxies across the sky, and the finer details in the ancient light left over from the Big Bang, both carry a faint imprint of how much the neutrinos smooth things out. By measuring that pattern with great care, cosmologists can work backward to how much the neutrinos must weigh. If neutrinos were heavier, the universe would look measurably smoother on small scales than it does. The maps of galaxies drawn by great surveys of the sky, and the maps of the ancient background light drawn by satellites, together let cosmologists set a limit on the combined mass of all three neutrino kinds. Remarkably, this cosmic method is even more sensitive than the direct laboratory scales. It suggests that the sum of the three neutrino masses is very small indeed, tighter than what a tabletop experiment has yet reached. The two approaches meet from opposite ends. Katrin weighs the neutrino by watching single atoms decay, 1 electron at a time, in a German laboratory. Cosmology weighs the same particle by reading the shape of the entire visible universe, drawn across billions of light years, and they broadly agree. The neutrino is extraordinarily light, its total mass a tiny fraction of the units physicists use. Small enough that it barely tilts the balance even when you weigh the whole sky. This agreement between the smallest measurement and the largest is one of the quiet triumphs of modern physics. The same faint particle, streaming through your body 100 trillion times a second, is heavy enough to shape the growth of galaxies, and light enough to slip past the finest scale we can build. But knowing roughly how heavy the three neutrinos are together still leaves a strange gap in our knowledge. We do not yet know how those masses are arranged. We do not know which neutrino is the heaviest and which is the lightest. Oscillation gave us a curious and frustrating kind of knowledge about the neutrino masses. It told us how they differ, but not how they stack. To see the puzzle, remember that there are three mass states, labelled 1, 2 and 3. By studying oscillations, physicists have measured two differences between them, or more precisely the differences between their squared masses, which is what the oscillation beats actually depend on. From the solar neutrinos, we know how far apart two of the mass states are. From the atmospheric neutrinos, we know how far apart another pair is, and this second gap is much larger than the first. So we have a small gap and a large gap. We know their sizes well. What we do not know is how they fit together into a single ladder, and the reason is subtle. The oscillation measurements tell us the sizes of the gaps, but for the large atmospheric gap, they do not tell us the direction. They cannot say whether the lone, widely separated mass state sits at the top of the ladder or at the bottom. This leaves two possible arrangements, and physicists have not yet been able to tell which one nature chose. In the first arrangement, called the normal ordering, the two closely spaced mass states are the lighter pair sitting low, and the third, widely separated state sits high above them, the heaviest of the three. The ladder climbs from a close pair at the bottom up to a lone rung far above. This is called normal, partly because it resembles the pattern seen among the other particles of matter, where each generation is heavier than the last. In the second arrangement, called the inverted ordering, the picture is flipped. The closely spaced pair sits high as the heavier two, and the lone, widely separated state sits far below them as the lightest of the three. The ladder has a lone rung at the bottom and a close pair up top. Both arrangements fit everything we have measured so far equally well. The oscillation experiments constrain the gaps, not their up and down order, so both the normal and the inverted ladder are still standing as live possibilities. This is the question of the neutrino mass ordering, and it is one of the genuine open problems in the field right now. It matters more than it might seem. The ordering shapes what we expect from other experiments, including the search for the neutrino's absolute mass and the deep question of whether the neutrino is its own antiparticle. If nature chose the inverted ordering, some of those other experiments should see a signal within a certain reach. If nature chose the normal ordering, the signal could be far smaller and harder to catch. So the ordering is a fork in the road, and several major experiments are being built partly to settle it. They will look at oscillations with new precision, using neutrinos sent through the Earth over long distances, and using the faint neutrinos from the sky to tease apart which ladder is real. There are early hints leaning one way, toward the normal ordering, but nothing yet certain, and an honest account has to leave the question open. We know the neutrino has mass, we know roughly how much all three weigh together, we even know the two gaps between them with fine precision, but we still cannot say for sure which neutrino is the heaviest. It is a plain reminder of how much remains hidden in this particle, and there is a deeper puzzle sitting underneath all of this, stranger than the ordering. Not how the masses are arranged, but why they are so unimaginably small in the first place. Step back and look at the neutrino's mass beside the masses of everything else, and something looks deeply wrong. Not wrong as in mistaken, but wrong as in unexplained, a number so far out of line that it cries out for a reason. Consider the other particles of matter. The electron is light, but the neutrino's mass ceiling is at least 500,000 times smaller than the electron. The heavier particles, like the top quark, are heavier still, millions of times heavier than the electron, and so hundreds of billions of times heavier than the neutrino. Line up all the particles of matter by weight, and they spread across an enormous range, but they cluster roughly within a few factors of each other in each generation. The neutrino sits far, far below the whole crowd, separated from even the next lightest particle by a gulf so wide it looks like a different kind of thing entirely. In the ordinary way, the standard model gives particles their mass. Every particle gets its weight from its interaction with a field that fills all of space. The Higgs field, discovered through its own particle at the Great Collider at CERN in 2012. A particle that couples strongly to this field is heavy. A particle that couples weakly is light. To make the neutrino as light as it is by this mechanism alone, its coupling to the Higgs field would have to be almost unimaginably tiny, far smaller than for any other particle, with no reason offered for why it should be so feeble. Physicists distrust numbers like that. When a quantity is not just small but wildly, inexplicably small compared to everything around it, they suspect that a different mechanism is hiding underneath, one that would make the smallness natural instead of accidental. And for the neutrino, there is a candidate mechanism, one of the most elegant ideas in modern physics. It is called the seesaw. The seesaw idea supposes that alongside the familiar light neutrino, there exists a second hidden partner neutrino that is extraordinarily heavy, far heavier than any particle we have found, perhaps near the energies of the very early universe. We have never seen this heavy partner, and with current machines we cannot make one. But if it exists, and if it mixes with the light neutrino in a particular way, the mathematics produces a striking result. The heavier the hidden partner, the lighter the visible neutrino becomes. The two are linked like the two ends of a seesaw. Push one end far up into enormous mass, and the other end sinks correspondingly low into the tiny mass we actually measure. The very lightness of the neutrino, in this picture, is not a fluke of a feeble coupling. It is the shadow cast by something huge. The neutrino is light precisely because its partner is heavy. This is why the seesaw is so appealing. It turns the neutrino's strange smallness from an awkward accident into a clue. It says the neutrino is light for a reason, and the reason is a new, heavy particle lying far beyond the reach of our machines, a piece of physics well outside the standard model. If the seesaw is right, then the faint neutrino streaming through you carries the fingerprint of energies from the first instant of the universe, scales we can reach in no other way. The idea cannot yet be proven, since the heavy partner is too massive to make, but it makes a testable promise about the light neutrino we can study. It predicts that the neutrino should be a very particular kind of particle, one that blurs the line between matter and antimatter, and that possibility raises one of the strangest questions we can ask about any particle at all. Here is a question that sounds almost like a riddle. Could a particle be its own antiparticle? For most particles, the answer is plainly no. The electron has an antiparticle, the positron, and they are clearly different. The electron carries negative charge, the positron carries positive charge, and when they meet, they annihilate in a flash of light. The charge is what tells them apart. An electron can never be mistaken for its own antiparticle, because its opposite has the opposite charge, and opposite is not the same. But the neutrino is different in one crucial way. It has no electric charge at all. It is perfectly neutral. And that removes the very thing that usually keeps a particle and its antiparticle distinct. Without charge, the bookkeeping that separates matter from antimatter grows blurry, and a strange possibility opens up. Perhaps for the neutrino, the particle and the antiparticle are not two different things. Perhaps they are one and the same, seen from different angles. This idea goes back to an Italian physicist named Ettore Majorana, a figure as mysterious as the question he raised. Majorana was a brilliant and reclusive member of Enrico Fermi's circle in Rome, spoken of with awe by those who knew him. In 1938, he boarded a ship and vanished without a trace, never to be seen again, his disappearance never explained. Before he vanished, he worked out the mathematics of a neutral particle that could be its own antiparticle. Such a particle is now called a Majorana particle in his memory. So the neutrino sits at a fork with two possibilities, and we do not yet know which is real. In the first, the neutrino is like the electron, an ordinary matter particle with a genuinely distinct antiparticle, the antineutrino. This is called a Dirac neutrino, after Paul Dirac, who first predicted antimatter. In the second, the neutrino is a Majorana particle, and the neutrino and antineutrino are two faces of a single thing, distinguished only by how they happen to be moving and spinning. In this case, there is really only one particle, wearing what look like two labels. The distinction is not a mere technicality, it reaches to the heart of what the neutrino is, and it ties directly to the seesaw idea from before. The elegant seesaw mechanism, the one that would explain why the neutrino is so light, works naturally only if the neutrino is a Majorana particle, its own antiparticle. If the neutrino turns out instead to be an ordinary Dirac particle, the seesaw loses much of its appeal, and the mystery of the tiny mass grows deeper again. So finding out which kind of neutrino nature made would tell us something profound. It would tell us whether the neutrino is truly a new kind of matter, unlike any other particle of substance, a thing that erases the line between matter and antimatter. And it might confirm the mechanism that makes it so light and point clearly to the heavy physics beyond the standard model. For a long time this looked like a question pure thought could raise but no experiment could ever answer. How could you possibly tell, from the outside, whether a neutral, barely interacting particle is secretly its own antiparticle? Yet physicists have found a way, at least in principle. There is one rare process in nature, almost impossibly rare, that could happen only if the neutrino is its own antiparticle. If that process were ever seen, even once, cleanly, it would settle the question. And so, deep underground, in some of the quietest and most shielded places on Earth, experiments are watching and waiting for a single decay that has never yet been seen. The process physicists are hunting for is a mouthful of a name, neutrinoless double beta decay, and it is worth unpacking slowly, because a single clean sighting of it would rank among the most important results in modern physics. Start with ordinary double beta decay, which is itself real and rare. In certain special atomic nuclei, a single beta decay is forbidden by the energy bookkeeping, but two beta decays happening at once are allowed. In this process, two neutrons in the nucleus turn into two protons at the same time, throwing out two electrons and two antineutrinos together. It is an exceedingly slow process, so slow that a sample of such atoms takes far longer than the age of the universe to half decay. But it has been observed, and it fits the standard model. Now imagine the same event with one difference. Two neutrons turn into two protons, two electrons fly out, but no neutrinos come out at all. This is the neutrinoless version. The two electrons appear, but the two antineutrinos are gone. And this can happen only under one very special condition. It can happen only if the neutrino is its own antiparticle, a Majorana particle. Here is the idea in plain terms. In the ordinary double decay, Each of the two transformations makes an antineutrino. But if the neutrino is its own antiparticle, then the antineutrino made in one of the two transformations can be absorbed, as if it were an ordinary neutrino, by the other transformation happening right beside it. The two neutrinos, being secretly the same kind of thing as their own opposites, cancel each other inside the nucleus. They are created and swallowed within the same event, and none escapes. Only the two electrons come out. So this neutrinoless decay is a kind of ghostly handshake, possible only if the neutrino can shake hands with itself. If the neutrino were an ordinary Dirac particle with a truly distinct antiparticle, the handshake could never happen, and this decay would be strictly forbidden. That is what makes it such a clean test. The presence or absence of this one process answers the deep question directly. See it, and the neutrino is its own antiparticle, a Majorana particle, and the seesaw picture gains powerful support. Never see it, down to extraordinary sensitivity, and the case for the Majorana neutrino weakens. The experimental signature is beautifully sharp. In ordinary double beta decay, the two escaping neutrinos carry off a variable share of the energy, so the two electrons together show a smear of energies, just like the old beta decay spectrum. But in the neutrinoless decay, with no neutrinos to take a cut, the two electrons must carry the entire fixed energy of the decay every time. So their combined energy would always land at one exact value, making a single sharp spike standing above the broad smear. Finding that spike is the whole game. The difficulty is the rarity. This decay, if it happens at all, is stupendously rare, rarer even than ordinary double beta decay, which is already among the slowest processes known. To have any chance, experiments gather large amounts of the special isotopes that can undergo it, and place them deep underground, wrapped in the most careful shielding humans can build, in the quietest conditions on Earth, to keep out every stray particle that might fake the signal. Experiments with names like Gerda, Camland Zen, and Quor have watched patiently, and larger ones are being built. So far, no one has seen the neutrinoless spike. The searches have only set limits, pushing the possible rate ever lower, telling us that if this decay happens, it is even rarer than we thought. The question remains open. But the stakes reach beyond the nature of the neutrino, into the very reason the universe contains anything at all. There is a fact about the universe so basic that it is easy to overlook, and yet no one fully understands it. The universe is made of matter. You are made of matter. The Earth, the Sun, the stars, the galaxies, all of it is matter, and almost none of it is antimatter. This seems unremarkable only because it is all we have ever known. But when you look at the laws of physics, it becomes a genuine puzzle, one of the deepest we have. The trouble is that matter and antimatter appear, in the laws, to be almost perfectly balanced. For nearly every particle of matter, there is a mirror antiparticle, with the same mass and opposite charge, and when matter and antimatter meet, they annihilate, vanishing into light. In the earliest moments of the universe, in the hot, dense fire after the Big Bang, energy was constantly turning into particles, and whenever energy makes particles, it makes them in pairs, one particle of matter and one of antimatter, in equal numbers. That is what the laws seem to demand. So the early universe should have been born with exactly equal amounts of matter and antimatter. But if that were the whole story, there would be no universe like ours at all. Equal matter and antimatter would have found each other as the universe cooled, and annihilated every particle meeting its opposite and vanishing into light. The cosmos would have ended up as nothing but a sea of radiation, with no leftover matter to make stars or planets or people. a perfectly balanced universe erases itself. Yet here we are. Something must have tipped the balance, very slightly, in favour of matter. The numbers physicists work out suggest the imbalance was tiny. For roughly every billion particles of antimatter in the early universe, there were about 1,000,000,001 particles of matter. The billion pairs annihilated, filling the universe with light. And that lonely 1 in a billion surplus of matter is everything that was left over. That leftover is us, and everything we see. All the matter in every galaxy is the faint residue of an almost perfect cancellation, the tiny surplus that survived because it had no antimatter partner left to annihilate with. So the question becomes sharp and strange. Where did that 1 in a billion advantage come from? What, in the first moments of the universe, favoured matter over antimatter by that razor-thin margin? For the laws to produce even a slight imbalance, they must treat matter and antimatter a little differently. There must be some process, somewhere, that is not perfectly even-handed between them. Physicists have a name for this needed asymmetry, and they have searched hard for where in the laws it could live. The standard model does contain a small built-in difference between matter and antimatter, seen in the behaviour of certain quarks. But when the numbers are worked through, that known difference falls far short. It is nowhere near enough to explain the surplus of matter that fills the universe. Something more is needed, some additional source of imbalance beyond what the standard model provides. And this is where the neutrino returns to the centre of the story, in perhaps its most profound role of all. For the neutrino is exactly the kind of particle that might carry the missing difference. If the neutrino is its own antiparticle, as the neutrinoless decay would show, and if neutrinos treat matter and antimatter a little differently, as their oscillations might reveal, then the faint ghost particle could be tied to the very existence of a material universe. The reason there is something rather than nothing might be written into the neutrino, and there is a specific idea for how that could work, reaching back to the first fraction of a second of time. The idea is called leptogenesis, and it is one of the most ambitious proposals in modern physics, tying the faintest particle we know to the origin of all matter. To follow it, we bring back the heavy neutrino from the seesaw, the hidden, enormously massive partner that made the ordinary neutrino so light. In the seesaw picture, these heavy neutrinos existed in the earliest moments of the universe, when temperatures were high enough to make such massive particles freely. They would have been created in the first tiny fraction of a second, and then, being unstable, they would have decayed away almost at once, leaving only their light cousins behind. Leptogenesis proposes that the decay of these heavy neutrinos is where the imbalance between matter and antimatter began. The key is that these heavy neutrinos, if they are Majorana particles, their own antiparticles, can decay in a lopsided way. A heavy neutrino can decay into ordinary matter particles, or into their antimatter opposites, and the crucial point is that it need not do both equally. If the laws governing the neutrino treat matter and antimatter even slightly differently, then the heavy neutrino will decay a little more often into matter than into antimatter, or the other way round. Out of a vast population of these heavy neutrinos decaying in the early universe, a small surplus of matter particles would be left over, specifically a surplus of the light particles called leptons, the family that includes the electron and the neutrino. This first imbalance is the seed. It begins as an excess of leptons, made in the decay of the heavy neutrinos. Then a second process, already part of the standard model, takes over. In the extreme conditions of the early universe, there is a mechanism that can convert an imbalance in leptons into an imbalance in the heavier particles that make up atoms, the protons and neutrons. So the lepton surplus from the neutrino decays gets partly turned into a surplus of ordinary matter. the very matter that would go on to form atoms, stars, and galaxies. The lopsided decay of heavy neutrinos in the first instant becomes. Through this chain, the reason there is any ordinary matter left in the universe at all. It is a breathtaking idea. It says that the origin of all the matter around you, every atom in your body, traces back to a subtle preference for matter over antimatter in the decay of neutrinos, in the first sliver of a second after the beginning. The ghost particle, in this telling, is not a minor detail of physics. It is the reason the universe is not empty. Leptogenesis is not proven. It rests on the heavy seesaw neutrinos which we cannot make or see directly, and on the neutrino being its own antiparticle, which we have not yet confirmed. It is a hypothesis, an elegant and serious one, but a hypothesis. Still, it makes the search for the neutrino's properties feel much larger than it might otherwise. When physicists hunt for neutrinoless double beta decay to learn whether the neutrino is its own antiparticle, they are also testing a key ingredient of leptogenesis. And when they look for a difference between how neutrinos and antineutrinos behave, they are looking for exactly the kind of matter-antimatter asymmetry the whole idea needs. That difference, if it exists, would show up in oscillation. A neutrino changing flavour and an antineutrino changing flavour might not do so at quite the same rate. If they differ, it would be the first sign in the neutrino of the very imbalance that leptogenesis requires. And so a new generation of experiments has set out to compare neutrinos and antineutrinos with great care, chasing that faint difference across hundreds of miles of rock. To look for a difference between neutrinos and antineutrinos, physicists build long baseline experiments, and the setup is grand in scale. At one end, a powerful accelerator produces an intense beam of neutrinos, aimed down into the Earth. The beam travels hundreds of miles straight through the rock, needing no tunnel, since neutrinos pass through solid ground as easily as through air. At the far end, a large detector waits underground to catch the few neutrinos that interact and to measure how many have changed flavour along the way. Crucially, these experiments can run the beam two ways. They can send a beam of neutrinos, measure how they oscillate, and then switch the machine to send a beam of antineutrinos and measure how those oscillate. If neutrinos and antineutrinos change flavour at exactly the same rate, then matter and antimatter are even-handed in this arena, and there is no help here for explaining the universe's surplus of matter. But if the two rates differ, even slightly, it would be direct evidence that the neutrino treats matter and antimatter differently, the kind of asymmetry that ideas like leptogenesis need. Two experiments have been leading this hunt. One is called T2K in Japan, which sends a neutrino beam from a laboratory on the east coast across the country to the great Super-Kamiokande detector, the same water tank that first proved atmospheric oscillation. The other is called NOVA in the United States, which sends a beam from Fermilab near Chicago, several hundred miles north to a detector in the state of Minnesota. Both have been comparing neutrinos and antineutrinos for years, patiently gathering their rare interactions. The measurements are difficult, and the beams are faint by the time they arrive, so the numbers of caught neutrinos are small, and the results so far are suggestive rather than conclusive. There are hints in the data that neutrinos and antineutrinos may indeed behave a little differently, with the difference described by quantity physicists called the CP violating phase. Some of the results lean toward a sizable difference, which would be encouraging for the matter-antimatter story. But the uncertainties are still too large to claim a discovery, and an honest reading leaves the question open. The hint is there, the proof is not, and the current experiments do not have quite enough neutrinos to settle it. This is where a much larger experiment enters, one now being built to bring the answer within reach. It is called DUNE, the Deep Underground Neutrino Experiment, and it is among the most ambitious physics projects of our time. It will fire an extremely intense neutrino beam from Fermilab in Illinois, more than 800 miles through the Earth, to an enormous detector filled with liquid argon, deep in a former gold mine in South Dakota, the same mine, as it happens, where Raymond Davis first found the solar neutrinos missing decades ago. There is a quiet symmetry in that. The place where the neutrino puzzle first appeared, in the counting of solar neutrinos, will host the detector meant to answer one of its deepest questions. June is designed to catch far more neutrinos than any experiment before it, and to measure the difference between neutrinos and antineutrinos with enough precision to know whether it is real. It should also settle the mass ordering, telling us at last which neutrino is the heaviest. If the neutrino does treat matter and antimatter differently, June has a strong chance of proving it, and of tying the ghost particle firmly to the reason the universe is full of something. But before we follow that thread to the end, there is another open question. One that asks whether we have even counted all the neutrinos correctly. Throughout this story we have spoken of 3 neutrinos, 3 flavors matched to the electron, the muon, and the tau. The measurement of the Z boson at CERN confirmed that there are exactly 3 light neutrinos of the familiar kind, and that number has held firm. But there is a loophole in that statement, and it hides a real and stubborn puzzle. The count of 3 applies only to neutrinos that feel the weak force. The neutrinos that take part in the ordinary interactions we can detect. The measurement counts only neutrinos that talk to the rest of matter through the weak force. It says nothing about a neutrino that might feel no force at all except gravity, a neutrino even more aloof and ghostly than the 3 we know. Such a particle would be invisible to the Z boson measurement and to nearly every experiment, because it would not interact through the weak force the way normal neutrinos do. Physicists call this hypothetical particle a sterile neutrino. Sterile because it is barren of even the faint weak interaction that lets ordinary neutrinos be caught at all. A sterile neutrino would be almost perfectly undetectable on its own. It would feel only gravity directly. But there is one way it could still betray its presence. If sterile neutrinos exist and mix with the ordinary neutrinos, then the 3 known neutrinos could sometimes oscillate into a sterile one and back, adding an extra pattern to the oscillations we already know. So even a particle that touches nothing could leave a fingerprint, by subtly altering how the visible neutrinos change flavour. And there are a few experimental results, anomalies that will not quite go away, that some physicists think might be exactly that fingerprint. The most famous came from an experiment called SEND at the Los Alamos Laboratory in the United States in the 1990s. SEND studied neutrinos over a short distance and found more flavour changing than the standard 3 neutrino picture allowed. The excess was small but statistically stubborn, and it hinted at oscillation happening faster than 3 neutrinos could produce, which could be a sign of a 4th sterile neutrino mixing in. The ill-send result was strange enough that physicists built another experiment to check it, called Mini-Boony at Fermilab. Mini-Boony ran for years looking in a different way at a similar range, and it too found an unexplained excess of events broadly in the same direction as LSEND. 2 experiments then saw something that did not fit the 3 neutrino world. But the sterile neutrino has not been confirmed, and the situation is genuinely muddy. The trouble is that other experiments, searching for the same sterile neutrino in other ways, have not found it, and some have ruled out the simplest versions of the idea that would explain SEND and Mini-Boon. A newer experiment at Fermilab, called Micro-Boon, examined the Mini-Boon excess with a finer detector and found no clear sign of the sterile neutrino behind it, though it could not fully close every possibility. So the anomalies remain unexplained, without a confirmed cause. This is science in its honest, unfinished state. There are real results that do not fit, and there is a candidate explanation, the sterile neutrino, that is elegant but unconfirmed and in tension with other data. It may be that a sterile neutrino is hiding there, a fourth kind of ghost even fainter than the rest. Or it may be that the anomalies come from something more ordinary that we do not yet fully understand about the experiments or the known neutrinos. The question stays open, and it is a reminder that even our count of the neutrinos may not be complete. Meanwhile, the neutrinos we do know have begun to serve a wholly different purpose. They have become a new way to see the universe. For most of this story, neutrinos have been the thing under study, the mystery to be solved. But neutrinos have also become a tool, a new kind of eye on the cosmos, and this turn began with a single unforgettable night in 1987. On the 23rd of February that year, in a nearby galaxy called the Large Magellanic Cloud, a massive star reached the end of its life and collapsed, then exploded as a supernova, one of the most violent events in the universe. The light from that explosion reached Earth and became visible in the southern sky, the closest supernova seen in centuries. It was named Supernova 1987A. But the light was not the first thing to arrive. When a massive star collapses, the vast majority of the energy released, around 99% of it, is carried away not by light but by neutrinos in an immense burst as the star's core crushes down. Those neutrinos poured out of the dying star and raced across space, and because they interact so weakly, they escaped the collapsing core immediately, while the light had to struggle out through the exploding layers over hours. So the neutrinos reached Earth first, a few hours ahead of the visible flash. And they were caught. In underground detectors built to study neutrinos, including the Kamiokande detector in Japan, and another called IM in the United States, a tiny handful of neutrinos from the supernova arrived within a span of seconds. About 24 neutrino events in total across the detectors from an explosion in another galaxy roughly 160,000 light-years away. 24 ghostly particles after a journey of 160,000 years caught in tanks of water deep underground. Those 24 events were a landmark. They confirmed, in one stroke, the basic theory of how massive stars die, showing that the collapse really does release its energy overwhelmingly as neutrinos, just as the calculations predicted. For a few seconds, physicists watched the core of a dying star directly, through the only messengers that could escape it intact. It was the birth of neutrino astronomy, the practice of studying the universe not by its light, but by the neutrinos it sends. Neutrinos carry a special gift as messengers. Because they pass through matter so easily, they travel to us straight from places light can never leave, from the crushed core of a collapsing star, from the heart of the sun, from regions wrapped in gas and dust that block all light. Light gets scattered, absorbed, and bent on its way across the universe. Neutrinos come to us in a straight line, unblocked and unchanged, carrying news from the most hidden places there are. To use this gift fully, physicists have built enormous neutrino telescopes, and the largest is astonishing. It is called IceCube, and it is buried in the ice at the South Pole. IceCube turns a cubic kilometre of clear Antarctic ice, 1 billion tons of it, into a single vast detector threaded with strings of light sensors deep below the surface. When a high-energy neutrino from space strikes the ice, it makes a flash that the sensors record, and from the pattern Ice Cube can tell where in the sky the neutrino came from. Ice Cube has caught neutrinos of enormous energy arriving from far outside our galaxy, from violent objects in the distant universe, including the blazing cores of galaxies with giant black holes at their centres. It has begun to map the sky in neutrinos, opening a genuinely new window on the cosmos. And this new astronomy points toward the oldest and faintest signal of all, a sea of neutrinos left over from the very beginning of time. There is a light that fills the whole sky, older than any star, called the cosmic microwave background. It is the afterglow of the Big Bang, the oldest light in the universe, released when the cosmos had cooled just enough to become transparent, about 380,000 years after the beginning. Before that moment, the universe was too hot and dense for light to travel freely, so no light survives from earlier. That ancient glow has been studied in exquisite detail, and it is one of our richest windows onto the early universe. But there is something even older than that oldest light, and it too fills the sky, though we have never directly seen it. It is a background not of light but of neutrinos, and it comes from a far earlier moment than the light does. Because neutrinos interact so weakly, they stopped bumping into the rest of matter and began to travel freely much sooner than light could. While light stayed trapped in the hot fog for hundreds of thousands of years, the neutrinos broke free after only about 1 second. So the neutrinos filling space today have been streaming unimpeded since the universe was 1 second old, carrying a picture of that first second from an era the oldest light cannot reach. This is the cosmic neutrino background, and it is the oldest whisper in the universe, older than the oldest light by hundreds of thousands of years. It surrounds us everywhere, a faint relic sea of neutrinos left from the first second of time. In every small volume of space, everywhere, there are hundreds of these ancient neutrinos, part of the vast population that lets even their tiny masses shape the growth of galaxies. They have been flying since almost the very beginning, cooled now to the faintest energies of any particles we know. We have very strong indirect evidence that this background is real. Its presence shows up in the detailed pattern of the oldest light, and in the way the light elements formed in the first minutes, both of which came out as they did, partly because of the neutrinos present at the time. The cosmic neutrino background is woven into the accepted history of the universe, and the fit is good. What we have not yet done is catch one of these relic neutrinos directly, and it is fearsomely hard, harder than any neutrino detection yet, because these ancient neutrinos carry so little energy. Every method we have used to catch neutrinos relies on the energy they bring to a collision, and the relic neutrinos, cooled by billions of years of the universe's expansion, have almost none. They are the faintest, gentlest particles imaginable, and detecting them directly is at the very edge of what physicists can conceive. There are proposals for how it might one day be done, using a target so sensitive that even a whisper-soft neutrino could trigger it, but no one has yet succeeded. To catch a relic neutrino would be to touch the first second of the universe directly, to hold in a detector a particle that has been flying since the cosmos was newborn. It would be, in a real sense, the oldest thing we have ever caught. That goal still lies ahead of us, but the fact that we can even speak of it, that we can describe a sea of particles from the first second and know it must be there, is a measure of how far the neutrino has carried us. From a desperate guess to save a broken sun, to a messenger from the birth of the universe, the neutrino has led physicists across the whole map of nature. It only remains to gather what all of these ghosts have been telling us, and to return to the question we began with. We began with your hand, and the flood of neutrinos pouring through it, 100 trillion every second, felt by nothing and stopped by nothing. And we asked a simple question: how can something so close to nothing be the first solid sign that our best theory of matter is not the whole story? We can now answer it plainly. The neutrino is the first sign because it has mass, and the standard model said it should not. That single fact, that the neutrino weighs a tiny stubborn sliver rather than nothing at all, was proven by watching neutrinos change flavour as they travel. In the atmosphere and from the sun, confirmed by great detectors under mountains and deep in mines. And because the theory was built with a massless neutrino woven into its foundation, the discovery of neutrino mass is a genuine crack, the one place where the most successful theory in science has been shown cleanly to be incomplete. The neutrino points beneath the standard model. That is the meaning of the title, and it is not a metaphor. It is the literal state of physics today. Nearly everything else the theory predicts holds to staggering precision, and yet here, in the lightest particle of all, the theory fails, and something more must lie underneath. The neutrino is our clearest doorway to that something more. Think of how much this one faint particle has touched. It was invented on paper by Wolfgang Pauli to save the law of energy, named by Enrico Fermi, and caught at last by Cowan and Reines beside a reactor. It multiplied into 3 flavours, went missing from the sun in Raymond Davis's tank, and revealed its shape-changing nature through the patient work of Pontecorvo's idea and the great detectors of Super-Kamiokande and Sudbury. It carries a mass so small we can barely weigh it, whether by the slow decay of tritium in Katrin or by the growth of the whole visible universe. It may be its own antiparticle, in the way Ettore Majorana imagined before he vanished. It may, in the first fraction of a second, have tipped the balance that left the universe full of matter rather than empty, the reason there is anything here at all, including you. And it reaches us from the cores of dying stars and from the first second of time. Sit for a moment with what that means for you, sitting here now. The neutrinos passing through you came from the heart of the sun, made in the same fusion that warms your face, arriving 8 minutes after they were born. Mixed among them are neutrinos from the atmosphere, from distant exploding stars, and a faint sea of them older than the oldest light, relics of the newborn universe, drifting through you unnoticed. You are not separate from this story. You are standing in the middle of it, crossed every second by particles that connect you directly to the sun, to the stars, and to the beginning of time. And these ghosts are telling us something. They are telling us that our picture of matter, for all its beauty and precision, is not finished. There is more physics beneath it, and the neutrino is the place where that deeper layer shows through. Why the neutrino is so light, whether it is its own mirror, how its masses are arranged, whether it is the reason the universe is not empty, these are among the great open questions, and the experiments being built now, June and its companions, are reaching toward the answers. So the next time you think of the empty space around you as truly empty, remember the flood passing through, silent and constant. The faintest things in the universe, the particles that barely exist, have turned out to be among the most important. The first to point past our best theory toward whatever lies beneath it. We followed the mystery down to its root, and found not an ending, but a door, held open by a ghost.